Good morning. Today we're going to cover chapter 1, which is the introduction to numerical methods. And here we're going to discuss the importance of numerical methods and why we're going to use them. In general, numerical methods will be used when we have complex mathematical problems that cannot be solved by hand. And some of these examples could be large systems of equations that have nonlinearities, integrations. Some of the commercial simulation software include this type of methods. Commercial numerical methods are coded in general with the most generic way of solving these problems. And sometimes if you have a particular problem that you want to solve, these type of commercial methods might be inefficient because they would just consider every possible situation. So sometimes it would be better to create your own algorithm that will be tailored by the type of problem that you have. Understanding the structure of the numerical methods also will allow you to choose the right algorithm. So if you have to solve a problem of, for instance, a system of equations or nonlinearities, there is going to be a number of potential methods that can be employed. And choosing the right one, it's important. Also, we're going to learn the limitations of these algorithms and when you should perhaps select one over another one. So now we're going to kind of present the different problems and chapters that we're going to study throughout the course. So just to give you a broad idea of the problems that we're going to cover. And in chapter 2 or part 2 of this course, what we're going to do is we're going to solve for the roots of equations. So if you have a function, and imagine that you have an extremely complex function, well, the roots of that equation will be those values where the function is going to be equal to 0. So x is going to be our independent variable, and we're going to provide different values to that independent variable x, and depending on the value, we're going to have different solutions for our function. So our goal is to find those values of x that will lead to a function that is going to be equal to 0. Another problem that we're going to do is linear algebraic equations. And in this case, we're going to have a system of equations. And in this example, we have two lines. And the problem is to find the intersection point of these two lines. So basically, it's going to be the set of values of x1 and x2 that will satisfy this system of equations. Another problem that we're going to solve is optimization. And this is when you have a function and our goal is to determine what would be the minimum value of that function and determine the value of x that provides that minimum value. Now, we've seen perhaps the first two cases in the past, even in grade 12 math, but we're going to make those problems more complex as we go. And it's not just going to be a single variable. Most likely, we're going to be dealing with multi-variable problems. And as you increase the complexity of the problem, then it will be more important the use of numerical methods. Other problems that we're going to see in the course is curve fitting. So if you have a data set, the problem is to find what would be the best fit, or what would be the function. Could be a linear function, could be a curve, could be like a second order polynomial or a third order polynomial that would fit the best these data points. So we're going to see and study how to determine those functions. Another one would be interpolation. So if you must pass through all these points, well, what would be eventually the function that will allow us to interpolate and determine the function itself. Then we're going to study integration, and in integration we're going to determine the area under the curve, and finally we're going to study ordinary differential equations, and here we're going to approximate what would be the slope of a curve at a particular point on the function, and we're going to approximate that to what is our differential term. Now, some of the problems that we're going to see might look a little bit simple. Some of the problems can actually be solved by hand, and they're not that hard to solve. However, by doing that, we're going to be able to compare what is the solution that we get analytically against the solution that we are getting using numerical methods. So we're going to make this comparison. But keep in mind that with numerical methods, you can have very, very complex problems, and you can still solve them using the algorithms that we're going to see in this course. So it doesn't really matter how complex the problem is, the application is going to be the same. Now, some of the problems that we're going to see in the course are going to be fairly straightforward, and the reason why we're going to do that is because our goal as well is to make a comparison of the algorithms and show how the algorithms are going to converge to a particular solution and how they work, and also we're going to look at the error that we get when using a particular algorithm. So numerical methods in engineering are very important. They can be applied in many disciplines of engineering. Engineers would, in general, understand a problem by observation and experimentation, or by using theoretical analysis and generalization. So when you define a particular problem, you're going to gather information by experimentation. You're going to get data. You're also going to apply the theory that defines the domain of the problem that you're solving, and you're going to establish a mathematical problem. So once you have these, which could be represented by a function, then you have to solve it. And in order to do that, you have to use mathematical tools, these algorithms, that will basically solve the problems numerically and determine what would be, for instance, the response of a system, or what would be a particular, what would be an optimized design for something that you're doing. And then once you get these results, then you can implement, you can build your prototype. You're going to get a better insight of what is affecting your system, and you can make the proper decisions and the educated decisions on how to proceed, how to continue your design, or how to eventually redesign something and continue from there. So in general, all the functions that we're going to be dealing with, that we're going to be using to model a physical problem, are going to be represented in this form. We're going to have a dependent variable, which in general is going to be the output, which is going to reflect the state of our system. And this is going to be a function of the independent variables, which are going to be our inputs, such as time and space. And then we're going to have even the initial conditions of our system. Then we're going to have the parameters that define the system, that are related or explain the characteristics of the system. And then we're going to have forcing functions, which are the external influence that is acting upon the system. So in order to explain that, we're going to talk about Newton's second law, and then we're going to solve a problem just to give you an idea of how we're going to implement numerical methods. Newton's second law states that the time rate change of a momentum of a body is equal to the resulting force acting on it. So if you remember, linear momentum is mass times velocity. So if we take the time derivative, then we get mass times acceleration, and that would be equivalent to all the sum of all the forces that are acting on the system. So we have force, which is the net force acting on the body. We have mass, which is the mass of the object, and A, which is going to be the acceleration. Now, Newton's second law has several characteristics that are typical of a mathematical model, and it describes a natural process or system in mathematical terms. It represents the ideal or simplified representation of reality, and finally it yields results that are useful and we can employ to predict what is going to happen in the system. So let's talk about a particular problem, and we're going to solve it using both the analytical solution and the numerical solution, and we're going to make a comparison of the results. Now, this is not going to be a difficult problem. This is something that we can solve analytically, and we're going to get the exact solution. But if we implement numerical methods, we're going to see what is the effect of some of the changes that we can make to the numerical method and how we can approximate better the response of the system. So let's assume that we have a parachutist that is coming down and releases the parachute, and we're going to model this problem using Newton's second law. So we have that the problem that we're trying to solve is to determine the terminal velocity of the parachutist. So as the parachutist jumps off the plane, he comes down, releases the parachute, and it's going to gain velocity. But there is going to be a point where the velocity will reach the maximum, and it's going to remain constant all the way to landing to the ground. So what we're going to do is, first of all, we're going to establish the forces that are acting on the system, and we're going to have two forces: the downward force, which is related to gravity, so we have the downward, which is m times g, and the other force that we're going to have is the upward force, Fu, and this is going to be related to the drag coefficient that we're going to have with the parachute. So if we combine these two forces and substitute them into Newton's second law, so you can see that is m times a equals f. We just sent m to the other side and represented the acceleration as the time derivative of the velocity. Then we get that the time derivative of the velocity is going to be equal to f, which is the downward force plus the upward force. But we, in our system of reference, we're going to consider positive going down. So we have mg minus cv divided by m. And this is going to be the equation that will represent the system. Now, we can simplify it in this form. So it's the only thing I did is cancel out the m's on the left hand side, and we have the g minus the drag, the coefficient of drag divided by m times the velocity. So what we got here is a differential equation. And the goal eventually is to determine over time, so if we evaluate this equation for a period of time, we're going to find that there is going to be a terminal velocity, which is going to become the steady state of the parachutist falling towards the ground. So if we apply calculus, and we're going to solve this problem by hand in a minute, we're going to reach the following equation. Okay, we're going to solve this problem of the parachutist analytically, and we're going to see that even though it's a simple problem, it does require quite a bit of algebra to derive eventually what would be the equation that will represent the velocity of the parachutist, and eventually how we can determine the terminal velocity. So this is the mathematical modeling. Okay, so by using Newton's second law, we derive that dv dt is going to be equal to g minus c over m times v. Okay, so what we're going to do next is we're going to isolate v, and this is just going to be to simplify the integration that we're going to carry out. So I'm going to factorize CMV. So we're going to multiply and divide by m and c, and it has to be negative. So m and c and times g plus v. So it's basically the same as what we have above, but now we're isolating the velocity, and it's positive. So now we're going to separate our terms, differential terms. And we get dv over, and we're going to divide this portion that we have here. So it's going to be minus m over c times g plus v, and this is going to be equal to, we have the time differential that will multiply that coefficient minus c over m. And now we can integrate. So if we integrate, we have and the integration of these eventually will lead to the natural logarithm of minus m over cg plus v equals, we're going to have minus c over m times t plus a coefficient. Let's call it c1 to differentiate from that c. And so now we can take the exponential on both ends to get rid of the natural logarithm, and we get minus m over c times g plus v is going to be equal to e to the minus cmt plus c1. If we apply some of the properties of exponentials, we can split the exponential. So we're going to have e to the minus c over mt times e to the c1. Okay, so now we're going to apply the initial conditions to figure out the value of c1. So at t equals 0, we're going to have an initial velocity that we're going to say that is equal to 0. So the initial velocity is going to be equal to 0. So we substitute that. So we're going to get velocity 0. So we have minus m over c times g is going to be equal to, we have e to the 0 is 1. So we have e to the c1. So now we know that e to the c1 is minus m over c times g. So now we can substitute these into our equation. So this is, let's call this one equation 1. And this is equation 2. Substitute equation 2 in 1. And we get minus m over c g plus v equals minus m over c times, now we're going to multiply by g. So we're substituting EC1, so e times e to the minus c over mt. Okay, so we just substituted that, and is what we get here. So now we can factorize m over cg, which is on both ends, and we can solve for the velocity. So we send that to the other side, and we're going to get, and I'm going to multiply it, or we're going to have m times g over c. This is positive, so it's going to be 1. This is negative, so it's minus e to the c over mt. Okay, so that is the equation that we saw. The velocity of the parachutist will be given by this equation. So what we have here is all the elements that we described before. We're going to have that the velocity is our dependent variable, and time is going to be our independent variable. So as time increases, the velocity will increase until it reaches that maximum velocity. Then there are going to be parameters that define the problem. So the mass of the parachutist, and also the coefficient of drag, which is related to the parachute itself. And then the forcing function is going to be gravity. That is going to be what is affecting the parachutist. So if we evaluate this function for a period of time, so we're going to tabulate from 0 time to infinity, although that eventually you can see that at a certain point we're going to reach a value that converges to a constant velocity. We can evaluate what is going to be that terminal velocity. So let's assume that the mass of the parachutist is 68 kilograms and the coefficient of drag is 12.5 kilograms per second. So if we substitute those values into our equation, we can determine for different values of t what is going to be the velocity. So in this tabulation, we substituted values of t, and we can see that the velocity will increase, but eventually it's going to converge to a certain value, which is going to be that terminal velocity of 53.4 meters per second. Now we're going to solve this problem numerically as well. And in order to do that, there are different types of algorithms. What we're going to do here is we're going to present perhaps the simplest of these algorithms. Later on in part 7, which is at the end of the course, we're going to see other algorithms that can be implemented to solve the same problem, and these algorithms are more robust than the one that we're going to see today. But this one will give you an idea of how we can evaluate the response of the system, how we can determine what the terminal velocity of the parachutist is. So we have our equation that represents the system, which is given by equation 1. And what we're going to do is we're going to approximate the differential term that we have here as delta V over delta T, which in this case is going to be the difference of the velocity at the next step in time minus the velocity at the previous step divided by delta T, which is the period that happened between those two steps. So T a step in the future minus the current step of time. So that would be our approximation. So this is going to be not exact. This is just a pure approximation that we're making. But by doing that, we're going to be able to evaluate what is going to be the value of the velocity in the future. So we substitute this relationship into our definition of the problem, and we get this expression. And from here, what we're going to do is we're going to isolate what is going to be the velocity at the next step, and we can move the rest to the right-hand side. And that will lead to this expression here. And what you can see is that the velocity, the new value of the velocity, is going to be equal to the previous value of the velocity plus the function that we defined here, which is going to be the slope. And the slope is because we have this function here is basically the time derivative of the velocity. That's why that is going to be this. Graphically, it represents the slope, and times delta t, or the step time that we're going to have during our numerical evaluation. Now, so we had the old value plus the slope times the step size, which is delta t. And this is going to be, for those who took MSc 380 with me, perhaps you remember that is Euler's method. And what is going to happen is that you start with an initial value of v. So when you jump, so most likely it's going to be zero velocity. And you're going to determine what is going to be the next value of the velocity by evaluating this portion. And then you're going to continue the evaluation, so it's going to be an iteration. So the new value now becomes the old value, and then you're going to evaluate this equation again, and you're going to get what would be the next value and so on. So you're going to create a loop for a period of time, and eventually you can graph what would be the velocity and how the velocity is going to change over time. Okay, so now we're going to solve the problem of the parachutist using the numerical solution. Okay, so what we know is the parameters of the problem. So we have mass, which is 68.1 kilograms. We have the coefficient of drag, that is 12.5 kilograms per second. And we have, of course, gravity, which is, let's call it, say it is 9.1 meters per square second. Okay? So what we're going to do is we're going to iterate our problem. And what we're going to do is we're going to implement the equation. I'm just going to write it down here. We're going to find what would be the velocity at the next step is going to be equal to the velocity at the previous step, plus we have the slope. In this case is going to be g minus c over m times v I times delta t. Okay, so that is the equation that we're going to employ. Now we start with I equals 0, so it's the initial velocity, and we're going to find the velocity at the next step. So we establish the initial condition, so the initial velocity is going to be 0, the initial time is going to be 0. We're going to say that delta t, which is the difference between t1 minus t0, is going to be 2 seconds, which is what the textbook used. And of course, t1 is 2 seconds, right? 2 minus 0 is 2 seconds. So now we can say that v1 is going to be equal to v0 plus g minus c over m v0 times delta t. And that is 0 plus 9.8 minus 12.5 divided by 68.1 times 0 times 2, and that is going to be equal to 19.6 meters per second. Now we go to I equals 1, and now the velocity that we're going to have here is going to be v1. So v1 is 19.6, which is what we found in the previous step. Delta t is always going to be 2 seconds, and t2 in this case is going to be 4 seconds. Okay, so t2 is just the valuation at 4 seconds, but the delta t is the difference between t1 and t2. So v2 is going to be equal to v1 plus g minus c over m v1 times delta t, and that is going to be equal to 19.6 plus 9.8 minus 12.5 divided by 68.1 times, I'm just going to do it here, times 19.6 times the delta t, which is 2. And that is 32.0 meters per second. And so we know, now we go to I equals 2, and that's the last iteration I'll do. And that leads to V2 is going to be equal to 32.0 meters per second. Then we have delta t, that is 2 seconds, and t3, which is 6 seconds. So now we defined V3, the velocity after 6 seconds, which is V2 plus G minus C over M V2, times delta t. So that is 32 plus 9.8 minus 12.5 divided by 68.1 times 32 times 2. And that is 39.85 meters per second. And so on. So we continue this process. Eventually, we're going to reach a value that is not going to change that much, that I think it was around 53, and that will be the terminal velocity of the parachutist. So the way that the numerical solution is implemented is that it uses the finite difference to approximate the first derivative of the velocity with respect to time. And at each iteration, what we're doing is we are approximating the slope. So if this was the shape of the function that actually we found analytically that it has that curvature, what we're doing is we're approximating, and that was our approximation using Euler's method. We said that the slope, which is the derivative of the velocity with respect to time, is going to be equivalent, or our approximation, to delta v over delta t. Now, you can see from this example what these two terms represent. The slope is going to be the tangent of the function at this particular point, at point t, and our approximation to that slope is going to be given by defining a particular delta t. Now, if we assume a large value of delta t, like in this case, we can see that our approximation is not going to be really good. So we're going to assume that this slope is going to be equivalent to that line that we have here. However, if we start reducing that delta t, so if we consider a point that is here, so the ti plus 1 is somewhere in between, so it's going to be somewhere here. So now the line is going to be much better or closer than what we had before. Now, if we consider perhaps delta t, where ti plus 1 is here, well, we're going to get even closer and closer. So the smaller we make that delta t, the closer we're going to be, or the closer our approximation is going to be. Now, we're going to see later that that might cause other type of errors. So the more computation that you're going to carry out, the more likely you're going to accumulate errors that can diverge from the actual solution. So making that step size extremely small is also not convenient. So there is a trade-off. So you have to be cautious on what that step size is going to be. But it gives you an idea of what the approximation is and how we can reduce the error that we can have in our simulation if we reduce the size of our step size. So this is the comparison between the analytical solution and the numerical solution. So in the analytical solution, which is the solid curve here, we can see that eventually it's going to converge to a terminal velocity. And the numerical solution had a fairly large step size of close to 2 seconds. And the approximations are defined by line. So we're going to have that after 2 seconds, we're going to reach that velocity. After 4 seconds, we're going to reach that velocity. So there is going to be this error between the two simulations. Now, if we reduced the step size, well, we're going to get a much closer representation of what the real or the exact solution of the problem is. So why do we care about solving problems numerically? Well, the problem of the parachutist was a problem that we could solve by hand analytically, and even though it was a simple problem, I mean, we had to basically solve the problem by hand and determine what the response was going to be. Now, most of the engineering problems are going to be fairly complex, and so we cannot find that analytical solution that will model the problem. So we have to rely on numerical solutions. So it is important to not only to understand how we can implement the numerical solutions, but also we have to be aware of the limitations, because sometimes the algorithms might diverge. So you have to be aware that that is possible. So you have to be conscious about it, right? And not rely always on the results, but be analytical and say, okay, if this is what I got, how can I improve, or how can I compare that result against something else? Is the result, the value that I'm getting, correct, or is there a way that I can prove that my solution is not correct? Now, there is going to be a variety of numerical methods that can be used. So sometimes it's good to test a couple of them to make sure that what you're getting is correct. So next, we're going to solve another problem. It's going to be another problem that is similar to the one that we solved before. This is a problem that we're going to solve during the live session tomorrow. And basically, the idea is to determine when a homicide happened, and this is going to be tested by determining the temperature of the body. So once you know the temperature of the body, then we're going to create a simulation that will define when that victim was killed. So we're going to employ this equation, which is Newton's law of cooling, and we're going to use Euler's method to evaluate the equation, and from there we're going to determine when the homicide happened. Okay, in chapter 2, what we're going to do is just briefly talk about the packages and programs that we can use to implement numerical methods. We're not going to go in detail. Now, there are different packages that can be used, like Excel or MATLAB, and some of them already have functions that are pre-built and can be used to solve the problems. Some of the functions are efficient. Some of them are very inefficient, especially depending on the problem that you're dealing with. And there are computer programs like C. These are high-level program languages where you would have to create your own algorithms to solve a particular problem. You can do the same in Excel and MATLAB, so you can create your own particular codes. And the importance of knowing how to create that algorithm is important because it depends on the problem that you're dealing with. Some of the pre-built functions that you might find in MATLAB, they are robust. So in general, they won't crash because they were designed for any type of problem. But there are multiple filters that will allow them to be robust. So if you have a problem that doesn't require all these filters, then that MATLAB function in general is going to be fairly slow. It's not something that you might be able to apply real time. And if your need is to apply something real time, then you would be better off by developing your own algorithm. So when you're programming, you have to be aware of the different structures and information that you will use when coding. So for example, you're going to have the simple information, which are going to be constants and variables, and the way that you're going to declare these variables could be a global variable or it could be a local variable. Now, one thing that it is a common mistake is to, and I've seen it so many times, to call the same variable twice. So you define it that, I don't know, A represents acceleration, and then eventually later on in the code you say, okay, A is going to be this constant. So it's no longer the acceleration, and just by doing that, you're basically making a big mistake, and you're going to have to debug it. And it is a common, very, very common mistake to make. Make sure that you keep track of your variables and your constants. There is going to be advanced information, so the way that we're going to structure multiple variables. It could be in the form of arrays, vectors, matrices, or just data sets that you're saving, or you can go beyond that and have cells and structures that is not a simple, and this is something that you do in MATLAB. It's you're defining a set of parameters for a particular value. So you might have matrices, and you might have other information embedded into a structure. Then you have mathematical formulas like assignment. Assignment is just the definition of, for instance, a variable. Then you have priority rules. So when you have an equation, you establish your brackets. You have to know what comes first. So if you have an addition and a multiplication, well, we know that we're going to multiply first and then we're going to add. So keep in mind about the priority rules and the use of brackets. Then we have intrinsic functions, which are functions that are already embedded in most of these pieces of software. I don't know how to take the square root of a number, so just the definition of the square root is an intrinsic function. Then we're going to have inputs and outputs. In some cases, outputs can be given in the form of a graph. Logical representation is sequence. So if you have a sequence of lines, how the flow of the program is going to go. Then we have a selection, which you might have filters like conditionals. If something happened, then do that. Otherwise, you do something different. Repetition, which could be a for loop or a while loop. And then modular programming, that you're going to have functions and subroutines. So, and this is very important when you're dealing with programming. So instead of repeating the same subroutines over and over, you can create a separate function that you are going to call multiple times. So you don't have to rewrite everything a few times, because if you found that you had a mistake in that subroutine, then you have to change it in every instance where you included that. So if you have a separate subroutine, you just change it once, but the way that you're going to call it is the same way. So the last two topics are kind of the most important in terms of definitions. So we're going to just briefly talk about them. So structured programming is going to be a set of rules that we're going to follow, and it is very important to be very well organized and structure your code properly. And this is because when you're working with other people, most likely you're going to share your codes, and it's good if you don't follow these rules and structure your code properly, then the other person is going to have trouble to understand what you're doing. Make sure that you add notes, so you can, when you share it, people can understand what you're doing in every line. Also make it that it's easy to debug it and test it. So sometimes even when you're testing your codes, and this is something that I usually do, I reach a point where I want to make sure that things that I wrote before are correct. So I might be able to provide a particular input that I know what the output is going to be and test it. And in many occasions, I would just leave it in the code, and I might comment it just to say, okay, I know that this should be the input and that should be the output. So at any moment, if I make some changes, I can go back and just test that. Okay, this is correct. So I can continue. Make sure that the code itself is well presented, especially that you can share it with other people. Now, there are going to be three fundamental structures. The sequence, this is how the instructions are going to be followed. So in general, if you just have a set of equations and a set of commands, then it will go line by line. Now, when you add a selection, then the code will split and will define some logical conditions. So if this happens, then do something. If that doesn't happen, do something else. And you can have multiple of these logical conditions. Then repetition is basically loops that will repeat until something happens. Either you have a counter that after doing that for a number of times, then it will stop, or you can have a function that will continue until that function reaches a particular value. So when we apply numerical methods, that is very common. So you're going to have either a value, for instance, if we're dealing with root finding and you want to reach the value of the function that is equal to 0, well, you're not going to reach the absolute 0. And you can create a function that you say, okay, I'm going to repeat that until I reach a value that is very, very close to 0. But of course, we're never going to get that absolute 0. Or you can do it that you compare the two values of your x, so there's the previous step and the current step, and then you compare the difference. And if you see that there is not too much change between the two of them, then you can stop your algorithm, and then you can output the value of the function. So another way that you can represent an algorithm is with flowcharts, and the definition of the symbols are given here. So this is a terminal, that is the flow lines, a process, input, output, a decision, a junction, an off-page connector, and a count-controlled loop. This is using flowcharts. What would be the comparison between a sequence and a selection? So in a sequence, as I mentioned, it's just going to be a number of instructions that you're going to provide, and the code is just going to read them line by line. In a selection, you're going to have a condition. So you start with your instructions, and once you reach that condition, if it's true, then it's going to do something. If it's not, then it's going to do something else. So it can either continue or perhaps do another type of instruction. And for repetition, when you have these loops, then what you're going to do is you go into that condition, and if it's, so this is an example of a while loop, then if that condition is true, you get out of the loop. If it's not, then you apply a particular instruction, and then you go back and repeat everything until you reach a condition where it is true, and then you get out of that loop. And finally, we have the for loop that in the same case is just going to, the instructions will take you to the for loop, and then you're going to look at, you would start a counter, and you're going to repeat the counter multiple times until it reaches a particular value, and then it's going to come out from that loop. Now, modular programming, we said that it is important. It is something that, and this is another thing that when we're learning to code, we don't consider. I remember when I was a student, for me it was much easier just to do copy and paste. And so if I had to repeat the same thing, I would just copy and paste. And then I realized that if I did something like that and then I had to make a change, then I had to make a change to everything. And if I missed one of the multiple copy and pastes that I made, then I was going to get an error. And debugging that error in general takes quite a bit of time. So you have to be aware of that. And the best solution to that is to create subprograms. So you're going to have a different function, a fairly structured and concise subprogram that is unique. So you can just, if you make a change here, you know that if you're going to repeat it multiple times, it will be the same every time. So another thing is that when you have these subprograms or separate functions, it's going to be much easier to debug it and test it. So if you share it to other people, it's going to be much easier to find what the errors are. And another thing that is important is some of these sub-functions can be used for other things as well. So you can create your own library with all these modules, and whenever you need that sub-function, then you can implement it. So for example, in some of the algorithms that we're going to study, well, we're going to have the physical problem that we're dealing with, our problem, and then we're going to have the numerical method. So if we say that the problem is root finding or optimization, let's use one, optimization. So you create your problem, and then you're going to send the value of your variables into the numerical method, so optimization, and it's going to give you the solution of that. Now, if you had it structured in a single code, well, that was kind of tailored for that problem, and you're not going to use it for another potential problem that you might have related to optimization. So if you have it as a separate file, then whenever you have to optimize something, you can use the same algorithm without having to change anything. It's basically you send the inputs, you get the outputs. Okay, so this is a pseudocode of what the problem of the parachutist could be. We're going to have a function called Euler, and this is where we're going to run Euler's method. And what the inputs are is the step size in terms of time, then the initial value of the independent variable. So most likely we're going to start at time equals 0, the final value of the independent variable, which is the final time, and the initial conditions of the velocity. Now, these lines just redefine the variables. In many cases, you would have them right here. So instead of having ti here, you would have t, and then this one is going to be tf remains tf, delta t it's here defined as h, and y I is going to be y. But we have it like that just to show what each of these parameters or variables are, and these are going to be the variables that we're going to use in the resolution of the problem. Then we're going to have a repetition, so we're going to have a kind of a while loop that do that until we reach the final time. And we're going to have in this particular section here what the condition is going to be for the final iteration. So if the current time plus the delta time, the step time, is greater than the final time, then basically you're going to stop your iteration. You're going to just run it one more time. That is going to be the new step time is going to be TF minus T. So you're going to reach that final time. And then we're going to have the subroutine of the slope, where we're going to establish what is going to be the approximation that we're going to have for the slope. And in the case of the parachutist, this is the part where we're going to introduce the drag coefficient and the mass. So basically our representation of how we establish our differential equation. And then once this one is established, then we're going to substitute it into Euler's equation. And then once we determine the new value of t, then we're going to find what would be the next step for the time, and we do the comparison if t is equal or greater than tf. If that's the case, you get out of the repetition of the for loop, well, while loop in this case, and then you continue. If not, then you continue repeating the repetition and Euler's method. So once you do that, then your solution, which is going to be the velocity, the terminal velocity, is going to be given. And this problem is, we can use exactly the same code to solve the crime scene, which we're going to see in the lecture. So programming in Excel is something that we do because it is convenient, especially because when we're dealing with problems where you just have to enter data and then everything just changes, all the cells are connected, and you establish your equation, so it is convenient to do it. I mean, when I have to record the marks of the students and I establish the function that defines the weights of every assignment, and which involves assignments, labs, exams, and so on. So I can provide a weight to each of these columns, write an equation, and establish what is going to be the grade for every student. So it is convenient. Excel has some built-in numerical capabilities that can be used, especially for curve fitting and optimization. Also, it has Visual Basic for applications, which it's a macro language that you can go beyond what Excel is capable of. You can start programming your own functions. And it does have several visualization tools that are useful, either in 2D and 3D. So this is the representation of the parachutist problem solved in Excel. So what we have here is each of these cells represent the parameters of the system, mass, and the drag coefficient. Then here we have the independent variable time. And then we can either, if you already solved the problem numerically, you can just enter the values, or you can even write your own equation. And so you would start and define what would be the velocity, the initial condition of the velocity, and then create an equation that will consider the parameters as well as the previous step of the velocity, the current state of the velocity, and the delta t, and then you evaluate what would be the next state of the velocity. And for the analytical solution, you would have something equivalent. You would create your own equation in this cell that will call what would be the mass of the parachutist, as well as the drag coefficient and the current time. And then the equation would be evaluated. And once you evaluate them, you can also plot the two graphs. So here we have the dashed line is the represents the analytical solution, whereas just the boxes represent the different values of the numerical solution. And in Excel, you can create by using Visual Basic a macro, and these are the commands that can be used to create conditions. These would be the commands that if you have a condition with multiple outcomes, then how to represent that. And these are similar, so conditions, multiple conditions that might happen, and this is the in case that you have cases, so you have a particular case, if that happens then you do something. If you have this other case and you have to select one of them, this is how to do a loop. And you have a control loop that it's basically a for loop that is repeating multiple times. So this is the pseudocode and how it would be structured using Excel. Now in this course we're not going to use Excel, but it's just a way to present that regardless of the program that you're using, the package that you're using, the structure is going to, it can be implemented. In MATLAB, you can go beyond that. MATLAB, it was developed to solve mathematical problems. And it does have a variety of numerical functions, and every new version of MATLAB, I think there are twice a year, there is a new version of MATLAB, so they improve their algorithms, they make them more robust, and it gives you tons of visualization tools that can be applied. And in MATLAB you can do a number of things. For example, these videos that you saw here are videos that were made by students in my courses of robotics. I asked the students to develop an animation using MATLAB, and in order to create that animation, they have to create what they do is they export parts from SolidWorks. So they draw their system in SolidWorks, and then they export the drawings into MATLAB. And each part of a drawing, it's a structure in MATLAB, and that structure would contain a number of information. So it would contain the location of the vertices, how these vertices form the surfaces, the color of that surface. So all that information is going to be embedded in a single element, which is a structure. And in MATLAB also we can implement the same type of commands or functions that we saw for Excel. You can have conditionals. If something happens or if something doesn't happen, then do something like that. And basically they are listed in this slide.